You look up at the night sky and everything feels calm, predictable, almost peaceful. The stars move slowly, the planets follow their paths, the sun rises where it should, sets where it should, day after day, year after year, like clockwork. But what if I told you one of those planets broke the rules? Not slightly, not by accident, but in a way that suggests something went very wrong. Imagine waking up tomorrow morning and the sun rises in the west. You'd panic. You'd think the laws of nature had just snapped in half on one world in our solar system. That's normal. And that world is closer to us than Mars, closer than most people realize. And yet, for thousands of years, we had absolutely no idea what it was really doing, because it was hiding something so strange that when scientists finally discovered it, they didn't believe their own data. They thought the instruments were broken. They thought the math was wrong. They thought nature itself couldn't possibly behave like this.
But it does.
And once you understand why, you start to realize something unsettling. This isn't just about one planet. This is a clue about violence, chaos, and hidden forces that shaped everything around us, including Earth. And maybe what could happen again. Let's start with something simple, something that feels obvious. Every planet spins. Earth spins. That's why we have day and night. It takes 24 hours to make one full turn. Mars, almost the same. Jupiter, it spins insanely fast, less than 10 hours, even though it's huge. That makes sense, right?
You expect planets to spin?
You expect them to behave in a certain way. But here's the first crack in that expectation. There's a planet where a single day lasts longer than its entire year. Think about that for a second. Not longer than Earth's year, longer than its own year. That means if you lived there, you would celebrate your birthday before the sun even finished crossing the sky once. Already strange.
But that's not the real problem.
The real problem is this. It spins the wrong way, completely backwards. If you stood on its surface, the sun would rise in the west, crawl across the sky, and set in the east. Everything you instinctively trust about how the universe works flipped. And here's the part that should bother you.
This isn't supposed to happen. Not just rare.
Not just unlikely. Physics says it shouldn't happen at all. To understand why, you need to go back in time, way back, before Earth existed, before the sun fully formed, back to a time when the solar system was just a cloud.
A massive, cold, silent cloud of gas and dust floating in space.
At first glance, it seems lifeless, motionless. But it isn't, because even in that quiet cloud, there's always a tiny bit of motion, a slight drift, a subtle rotation, maybe caused by a nearby star passing long ago, maybe triggered by a distant explosion, a supernova sending shock waves through space. It doesn't matter how it started. What matters is this.
Once that cloud has even the smallest amount of rotation, it can never get rid of it.
Ever. This is one of the most powerful rules in physics. It's called conservation of angular momentum, and it's ruthless. It doesn't negotiate. It doesn't fade away. It doesn't forget. It simply says, whatever rotation you start with, you keep forever. Now here's where things get interesting. That giant cloud begins to collapse under gravity.
Slowly at first,
then faster. As it shrinks, something strange happens. It spins faster. You've seen this before, even if you didn't realize it.
A figure skater pulling their arms inward suddenly spins faster.
Same energy, same person.
But smaller radius, faster rotation.
The cloud does exactly the same thing. It tightens, it accelerates, and eventually it flattens into a spinning disk. At the center, the sun begins to form. Around it, a vast rotating disk of dust and gas. This is where planets are born, and here's the key detail. Everything in that disk is moving the same way. Same direction, same rotation, same cosmic spin signature. That means every planet that forms from this disk should inherit that motion. They should orbit the sun in the same direction. They should spin in the same direction, like cars on a racetrack, all moving clockwise or counterclockwise together. And when we look at the solar system, that's exactly what we see. Earth spins one way, Mars spins that way. Jupiter spins that way. Saturn too.
Even the sun itself spins that way.
It's like a family resemblance, a shared origin,
a cosmic fingerprint.
So when you find one planet that doesn't follow that rule,
it's not just unusual.
It's suspicious, because reversing that motion isn't easy.
It's not like flipping a switch. Like
you're talking about a massive spinning object, weighing billions of trillions of tons, already in motion. To stop it, reverse it, and send it spinning the opposite direction.
You need something extreme,
something violent, or something incredibly persistent.
There are only two possibilities.
Either something hit that planet,
Hard enough to flip it,
or something has been slowly, quietly twisting it for billions of years, and a sudden crime,
or a slow conspiracy.
And here's where the mystery deepens. Because that planet,
The one that breaks the rules,
the one that spins backwards, is Venus,
the brightest object in the sky after the sun and moon,
visible to ancient civilizations, studied for thousands of years, and yet
we had no idea what it was really doing. Not until very recently.
For most of human history, Venus was a mystery wrapped in light.
You could see it easily,
but you couldn't see anything on it. No surface, no details, just a bright, glowing sphere.
That's because Venus is covered in something almost impenetrable.
A thick atmosphere, not like Earth's, much thicker, much denser, much more dangerous. If you tried to stand on Venus,
You wouldn't just suffocate.
you wouldn't just burn, you'd be crushed. The pressure at the surface is about 90 times stronger than Earth's.
That's like being deep underwater without protection.
And the temperature? Hot enough to melt metal.
Hotter than an oven. Hotter than you can imagine.
All caused by a runaway greenhouse effect, linked to greenhouse effect taken to its extreme. The atmosphere is mostly carbon dioxide, trapping heat relentlessly. And above it, clouds of acid. Not water, acid.
You can't see through it.
Light can't penetrate it. For centuries, scientists tried. They pointed telescopes at Venus
And saw nothing, just a blank white disk.
No rotation, no surface features, no clues. It was like the planet was hiding something. And in a way, it was. Then in the 20th century, everything changed. We developed a new tool,
Not based on light,
but on radio waves, radar. Instead of looking at Venus, we bounced signals off it.
signals that could pass through the clouds
Reached the surface,
and return.
carrying information. This was a breakthrough.
For the first time, we could see Venus. Not visually,
But physically, we could measure its motion, its rotation, its secrets. And what we found
didn't make sense.
At first, scientists thought there must be a mistake, because the data showed something impossible.
The surface wasn't rotating the way it should. The signal shifts, tiny changes in frequency, revealed motion.
One side moving toward us, the other moving away. But the pattern was reversed.
The planet wasn't spinning like the others, it was spinning backward.
Slowly, painfully slowly, taking longer to rotate once than to go around the sun.
It was like discovering a clock where the hands move in reverse. Not broken,
Just wrong. And when the results were confirmed,
there was a moment of silence in the scientific community.
because this wasn't just a curiosity, this was a problem, a serious one. Because physics doesn't like exceptions.
When something breaks the rules,
It usually means one of two things. Either we misunderstood the rules, or something extraordinary happened. And in this case, the rules were solid,
which meant
something happened to Venus. Something big, something violent, or something patient. And here's the twist. Even today, we don't know which one it was.
we have theories,
We have simulations, we have clues,
but no final answer, no smoking gun.
no certainty, just possibilities. And each possibility tells a different story, a different version of the past. Some of them involve collisions so powerful they could reshape planets. Others involve invisible forces, acting over billions of years, quietly rewriting motion itself.
And
Both are terrifying in their own way, because both are real, both exist, and both could happen again. So the question becomes,
what really happened to Venus?
was it struck by something massive, flipping it upside down like a coin? Or was it slowly twisted over billions of years by forces we barely notice?
And more importantly,
If something like that could happen to Venus, what does that say about Earth? Because we like to think
our world is stable.
predictable, safe. But the truth is,
We're part of the same system. We're born from the same disk.
following the same laws. And if one planet can break the pattern, then maybe the pattern isn't as safe as we think. Now, let's examine the first possibility, the violent one, the one that sounds like science fiction, but is actually grounded in reality.
A collision.
Not a small one, not an asteroid,
But something much bigger. A protoplanet.
an object the size of a world. Because early in the solar system's history, things were chaotic. Planets weren't neatly arranged. They were forming, growing, colliding, destroying each other.
It was a cosmic battlefield. And we know this for a fact.
Because something like this already happened. To Earth. Long ago, a massive object collided with early Earth. The impact was so powerful, it blasted material into space. That material eventually formed the moon. Yes, Our moon is likely the result of a planetary collision. So if that could happen here,
Why not on Venus?
imagine a massive object slamming into Venus at just the right angle. Not directly head on, but slightly off. Enough to transfer energy, enough to twist motion, enough to flip it, like hitting a spinning top from the side. You don't just stop it, you change how it spins. If the impact is strong enough, you could tilt the planet.
Even flip it nearly upside down
And that's exactly what we observe. Venus is tilted almost completely over, which means maybe it didn't reverse its spin,
maybe it was flipped.
and now it only looks like it's spinning backward. That's a subtle difference, but an important one because it changes the entire story. It means Venus didn't break the rules. It was forced into a new orientation by violence, by impact, by chaos, and that explanation is satisfying. It's simple, it's dramatic. It fits what we know about the early solar system. But there's a problem, a big one. If a massive collision happened, where's the evidence? Because when Earth was hit, we got the moon, a giant unmistakable scar, visible every night. But Venus? Nothing. No moon, no debris, no obvious sign of a massive impact.
It's like a crime scene with no weapon.
No fingerprints, no witnesses. And that's where the story becomes even more unsettling. Because if the violent explanation doesn't fully work, then we're left with the other possibility.
The quiet one.
The slow one, the one that doesn't happen in a moment, but over billions of years. And in some ways, that's even more disturbing because it means
A planet doesn't need a catastrophic event.
to completely change its behavior. It can happen slowly, silently, right under your nose, and you wouldn't even notice until it's too late. I'll take you into that possibility next, and it might completely change how you think about planets, atmospheres, and even Earth itself. Now consider the second possibility, not the violent, explosive kind that leaves behind obvious scars, but something far more subtle, far more patient, and in many ways far more unsettling. Imagine a force so quiet that at any given moment it feels insignificant, something you would never notice in a single lifetime, something that doesn't crash into a planet or tear it apart, but instead whispers to it, nudges it, over and over again for billions of years. This is where the idea of tides enters the story, but not the kind you're used to, not oceans rising and falling under the moon's pull. Venus doesn't even have oceans. What it does have is something far more powerful, an atmosphere so thick, so massive, that it behaves almost like a second body wrapped around the planet. To understand what that means, you have to shift how you think about air. On Earth, the atmosphere feels light, almost negligible. You don't think of it as something that can move planets. But on Venus, the atmosphere is crushing, dense enough to act like a slow-moving ocean of gas, pressing down with immense weight. Now bring in the sun. The sun's gravity doesn't just hold Venus in orbit, it pulls on it, gently, continuously. That pull stretches the planet ever so slightly, creating what physicists call a tidal bulge. Picture squeezing a rubber ball between your fingers. It elongates. The same thing happens to Venus, except the force doing the squeezing is gravity, and the deformation is incredibly small but very real. Now here's where things begin to twist. If Venus were not rotating, that bulge would always point directly at the sun. But Venus does rotate, even if very slowly, so the bulge doesn't line up perfectly. It gets dragged slightly ahead or behind, depending on the motion. And because it's misaligned, the sun's gravity pulls on that bulge unevenly, creating a torque, a twisting force. This is not speculation, it's a well-understood phenomenon tied to the same underlying physics as conservation of angular momentum. And that torque acts like a brake. It tries to slow the planet down, to reduce its rotation, to eventually lock it so that one side always faces the sun. We see this elsewhere. Our moon is tidally locked to Earth. One face always looks at us. Mercury is almost locked to the sun in a special resonance. So you might expect Venus to end up the same way, frozen with one side in eternal daylight. But it didn't. Instead, it went the other way, literally. And this is where the atmosphere changes everything. Because while the solid body of Venus is being tugged by gravity, the atmosphere is doing something completely different. The sun heats Venus, but not evenly. The side facing the sun gets blasted with energy, while the other side cools. That creates temperature differences, pressure differences, and movement. But here's the key. The atmosphere doesn't respond instantly. It has inertia. It takes time to heat up and cool down. So the hottest region isn't directly under the sun, it lags behind. That means the thick atmospheric mass forms its own kind of bulge, not aligned with the sun, but shifted. And now you have two competing effects. The solid planet's tidal bulge pulled one way, and the atmospheric bulge pulled another. Two forces, two torques, opposing each other in a silent battle that no human eye could ever see. The solid body wants to slow down and lock. The atmosphere wants to push it, but in the opposite direction. And over immense stretches of time, that tiny difference accumulates. This is the part that's hard to grasp, because our intuition fails us. We think in terms of seconds, minutes, years. But planets evolve over millions, billions of years. A tiny force applied constantly becomes unstoppable. It's like placing your hand on a spinning wheel and applying the slightest pressure, not enough to stop it immediately, but enough that over time it slows, stops, and then, if the force continues, begins to move the other way. That's what may have happened to Venus. Not a sudden flip, not a catastrophic event, but a slow reversal, a cosmic tug of war where the atmosphere gradually won. And here's the eerie part. This isn't just theory pulled out of thin air. Scientists have modeled this. They've run simulations accounting for the density of the atmosphere, the heating patterns, the gravitational interactions, even the internal structure of the planet. And what they find is deeply intriguing. Under the right conditions, a planet like Venus naturally evolves toward a state of slow retrograde rotation, not by accident, not by randomness, but as a stable outcome, like a marble rolling into a valley and staying there. There are multiple possible valleys, multiple stable states a planet can end up in, but Venus seems to have settled into one of the backward ones, and that means something profound. It means Venus didn't necessarily need a violent past to become what it is. It could have arrived there quietly, inevitably, as a result of physics playing out over time. That challenges something deep in how we think about the universe. We like dramatic explanations, explosions, impacts, collisions. They feel satisfying. They give us a clear cause and effect. But this is different. This suggests that even in the absence of chaos, strange things can emerge. That order itself can produce outcomes that look like accidents. And if that's true, then Venus isn't just a victim of some ancient catastrophe. It's a demonstration of how complex systems evolve, how small forces interacting over time can produce something completely unexpected. And suddenly, the mystery shifts. It's no longer just what happened to Venus. It becomes how many other worlds have been quietly reshaped in ways we don't yet understand. Because if an atmosphere can do this, if it can alter the spin of an entire planet, then what else can it do? And what does that say about our own world, where the atmosphere is changing even now in ways we're only beginning to grasp? But before you settle on that explanation, before you decide the mystery is solved, there's something else you need to consider, something that makes this even more complicated, even more unsettling, because the truth is, neither explanation fully satisfies all the evidence. The collision theory explains the tilt, but lacks clear physical traces. The atmospheric tide theory explains the rotation, but depends on very specific conditions and assumptions. And when scientists dig deeper, they find something frustrating. Multiple scenarios can produce the same result. Different histories, different starting points, all leading to the Venus we see today. It's like trying to solve a crime where every suspect has a plausible story and none of them can be ruled out. That's not how we like our science. We want clarity. We want a single, elegant answer. But sometimes nature doesn't give us that. Sometimes it gives us ambiguity. And in that ambiguity, something even more interesting emerges. Because when you can't pin down a single cause, you start to realize that the system itself is more flexible than you thought, more sensitive, more unpredictable. Venus might be the result of a collision, or slow atmospheric torque, or even a combination of both. Imagine that. A planet that was first knocked off balance by an impact then gradually pushed into its current state by atmospheric forces. A layered history, a sequence of events, each building on the last. That's not just a possibility, it might actually be the most realistic scenario. And if that's true, then Venus becomes something else entirely. Not an anomaly, but a record, a fossil of processes that were once common in the early solar system. A reminder that the neat, orderly arrangement we see today is the result of billions of years of evolution, not the starting point. And this leads to a deeper, more uncomfortable thought. Earth went through the same chaotic beginnings. It experienced impacts, shifts, changes. It developed an atmosphere, oceans, life. But what if things had been slightly different? What if Earth had ended up closer to the sun? What if its atmosphere had thickened instead of stabilizing? What if its rotation had been altered slowly or violently until it no longer behaved the way it does now? You start to see how narrow the path really is, how many things had to go just right for Earth to become what it is, and how easily it could have gone the other way. Venus might not just be a mystery, it might be a warning, a demonstration of how a planet can drift into a completely different state, not through a single catastrophic event, but through the accumulation of small, relentless forces. And that idea extends beyond just rotation, because Venus didn't just end up spinning backward, it also became a hellish world with temperatures hot enough to melt metal, pressures that crush anything that lands there, and an atmosphere that traps heat in a runaway version of the greenhouse effect. All of these features are connected. The rotation affects the atmosphere affects the temperature affects the chemistry. It's a network of feedback loops, each reinforcing the others. And once a planet enters that kind of state, it's incredibly hard to reverse. That's another lesson hidden in Venus. Not just how things change, but how they lock in. How a system can reach a point where it stabilizes in a configuration that seems extreme, but is actually self-sustaining. So now, when you look at Venus, you're not just looking at a planet that spins the wrong way. You're looking at the outcome of a complex, intertwined set of processes, some violent, some subtle, all interacting over unimaginable timescales. And the most unsettling part is this: we're still not entirely sure which processes mattered most. Even with modern science, advanced simulations, and decades of study, Venus refuses to give us a simple answer. It remains ambiguous, and that ambiguity is not a weakness of science, it's a reflection of reality. The universe doesn't always present us with clean, simple stories. Sometimes it presents us with puzzles that force us to think deeper, to question assumptions, to accept that multiple explanations can coexist. And in doing so, it reveals something more important than any single answer. It reveals how the system works, how delicate the balance is, how easily it can shift, and how even something as fundamental as the direction a planet spins is not guaranteed. It's earned, it's shaped, it's the result of history. And that means the story isn't over yet, because there are still pieces we haven't examined, clues we haven't fully understood, and one final possibility that might tie everything together in a way that's even more surprising than anything we've discussed so far. There's one more layer to this story, and it might be the most unsettling of all. Not because it gives us a clean answer, but because it forces us to accept that the universe doesn't always behave in a neat, predictable way. Up to now, you've been thinking in terms of causes. Something hit Venus, or something slowly twisted it. But what if the truth isn't one or the other? What if the real answer is that Venus didn't need a single defining event at all? What if it evolved into its current state through a combination of influences, each one small on its own, but together powerful enough to reshape an entire world? This is where modern planetary science begins to move away from simple explanations and toward something more complex, something more realistic. Because when scientists simulate the early solar system, not just one scenario, but thousands, they start to see a pattern. Not a single path, but many possible paths, all leading to similar outcomes. In some simulations, Venus begins spinning normally, like Earth, and then atmospheric tides gradually slow it down and reverse it. In others, it gets nudged by gravitational interactions with neighboring planets. tiny shifts in orbit that alter how solar energy is distributed across its surface. In still others, a moderate impact, not big enough to leave obvious scars, changes its tilt just enough that atmospheric effects take over from there. None of these events alone fully explain Venus, but together they form something like a story, not a single dramatic moment, but a long chain of influences, each one shaping the next. And this is where the idea becomes uncomfortable, because it means Venus might not be an exception. It might be a natural outcome. Not common, perhaps, but not impossible either. And if that's true, then the direction a planet spins is not guaranteed. It's not locked in at birth. It's something that can evolve, change, even reverse, depending on the conditions. That challenges one of our deepest assumptions, that the large-scale behavior of planets is stable, predictable, and permanent. But Venus suggests otherwise. It suggests that even something as fundamental as rotation can be altered, given enough time and the right combination of forces. And once you accept that, your perspective shifts, because you start to see planets not as fixed objects, but as dynamic systems, constantly evolving, constantly interacting with their environment. And those interactions don't stop once a planet forms. They continue quietly for billions of years. The sun keeps pulling, the atmosphere keeps circulating, internal heat rises and falls. Even the core and mantle exchange energy, affecting how the planet responds to external forces. It's a living system in a sense, not alive like a biological organism, but active, responsive, changing. And in that system, small differences matter. A slightly thicker atmosphere, a slightly different orbit, a slightly different initial spin. Any of these could push a planet down a completely different path. This is what scientists call sensitivity to initial conditions, a concept closely related to chaos theory, where tiny changes can lead to dramatically different outcomes over time. And Venus may be one of the most striking examples of this in our solar system, because when you compare it to Earth, the similarities are almost eerie. They're nearly the same size, nearly the same mass, formed from the same region of the protoplanetary disk, and yet they ended up completely different. Earth became a world of oceans, clouds, and life. Venus became a furnace, hot, dense, and hostile. And part of that difference may come down to something as subtle as how each planet spins, because rotation affects everything. It determines how heat is distributed, how winds circulate, how weather systems form. On Earth, a relatively fast rotation creates a complex system of atmospheric currents, jet streams, trade winds, storms that help regulate temperature. On Venus, the slow backward rotation produces a completely different pattern. Its atmosphere moves in a phenomenon called superrotation, where the upper layers circle the planet much faster than the surface itself. Winds high above Venus can complete a full circuit in just a few days, even though the planet takes months to rotate once. That's not just strange, it's extreme. And it's directly tied to how Venus spins. So now you have a feedback loop. The atmosphere influences the rotation, and the rotation influences the atmosphere, each one reinforcing the other, locking the planet into its current state. And once that loop stabilizes, it becomes very hard to break. That's why Venus remains the way it is today, not because it's stuck, but because it has settled into a configuration that is internally consistent, stable, self-sustaining. And that brings us to the final, deeper realization. The mystery of Venus isn't just about the past, it's about possibility. It's about what can happen when complex systems evolve over long periods of time. And it's about how little it takes to push those systems in a completely different direction. Because if Venus had started with slightly different conditions, if its atmosphere had been thinner or its rotation faster, it might have ended up more like Earth. And if Earth had been slightly different, it might have ended up more like Venus. That's not speculation. That's a real possibility supported by models of planetary formation and climate evolution. And that's what makes this so powerful, because it means the difference between a habitable world and an uninhabitable one might come down to a handful of variables interacting in ways we're only beginning to understand, and one of those variables is rotation. So now step back and look at the bigger picture. You started with a simple question: why does one planet spin backward? But what you've uncovered is something much deeper. You've uncovered a story about how planets form, how they evolve, and how they can change in ways that defy our expectations. You've seen how a basic principle like conservation of angular momentum sets the stage, but doesn't dictate every outcome. You've seen how forces like gravity and atmospheric dynamics can compete, interact, and produce results that seem almost impossible. And you've seen how the greenhouse effect can transform a planet's environment, turning a potentially Earth-like world into something entirely different. But perhaps the most important thing you've seen is this: the universe is not static. It's not fixed. It's not guaranteed to behave the way we expect. It's a system of interactions, feedback loops, and long-term evolution. And in that system, even the most fundamental properties, like the direction of a planet's spin, can change. That realization should stay with you, because it doesn't just apply to Venus. It applies to every planet, every system, every process in the universe, including our own. Earth feels stable because we experience it on human timescales, days, years, centuries, but on geological timescales, millions, billions of years, it is just as dynamic as Venus once was. Its rotation has changed before. Its atmosphere has changed dramatically over time. Its climate has shifted, sometimes rapidly, sometimes slowly, and it will continue to change. That doesn't mean Earth will suddenly flip or become uninhabitable overnight, but it does mean that the conditions we take for granted are not permanent. They are the result of a long chain of events balanced in a particular way for now. And that's the real lesson hidden in Venus. Not just that it spins backward, but that it could. That the laws of physics allow for such an outcome under the right conditions, and that those conditions are not as rare or as extreme as we might like to believe. Venus is not a glitch. It's a possibility realized, a demonstration of what can happen when a system evolves along a different path. And once you understand that, you start to look at the night sky differently. You start to see each planet not just as a distant object, but as a story, a history of interactions, choices, and consequences written in motion and matter, and you begin to realize that our own story is still being written. The forces that shaped Venus are still at work. Gravity still pulls. The sun still radiates energy. Atmospheres still circulate. And over long enough timescales, those forces can reshape worlds. The question is not whether change will happen, it's how and how much. And that brings us back to where we started, a simple, unsettling image, the sun rising in the west. On Venus, that's just another day, but on Earth, it would mean something had gone profoundly wrong. And now you know that kind of change is not beyond the laws of physics. It's not forbidden. It's just unlikely, given our current conditions. But conditions change, slowly, quietly, over time. And sometimes the universe doesn't need a dramatic event to create something extraordinary. Sometimes all it needs is time.